So this is a problem about a pendulum, and this is really more oscillations kinds of problems. This one's different though because instead of having linear motion back and forth with some x and acceleration a, now we're going to have some angle theta. So I'm going to start this problem by doing it in x and y components, but then after the break we'll look at how you might do it also in terms of angular components. So we'll start by making a free body diagram. There's some tension that goes along the rope, and there's some gravitational force that's downward. And it turns out that it's much easier to do this problem if we choose axes that go this way, x and y, that are tilted. So we'll take the gravity and break it into components along those two directions. And so the sum of the forces in the y direction, we'll start there, that's equal to the force of tension minus mg cosine theta, where this angle here is theta. And that's going to be equal to 0. The acceleration in the x direction is simply mg sine theta, and that's equal to ma. Okay, so a couple things we have to think about. The first is that if this is just a general pulling a mass on a rope to the side at any initial angle, this isn't simple harmonic motion, because we can't make what's on the left here look like just a simple displacement. However, if we have small angles, then we can use the small angle approximation, where sine theta is very close to theta. In other words, if I make a plot here of sine theta, what I'm saying is this region in here, this is very, similar to a straight line, but remember, this is radians only, because sine of 10 degrees is not 10. Okay, so once we've done that, then we'll rewrite as mg theta is equal to ma. Now let's think about what m means, and our goal is to write a in terms of theta. That's the only way we're going to recognize that it's simple harmonic motion. So let's think about this. Well, usually we write a as d squared x dt squared. That's actually true in this case. You should notice, though, that as the thing swings, if I always orient my axes along the string, it means that the direction of x is always going to be changing. Maybe it would make more sense to write it as d squared s dt squared, where this is now the arc length that it's traveling. Squared. So if we write it as that, then we know that the arc length is equal to the radius of the circle times theta. Oh, so that means that we can write the acceleration as L times d squared theta dt squared. This is a bit of a fine point, but you should notice that as the thing is swinging in the positive x direction, theta is actually decreasing. So because positive x now means negative displacement in theta, we have to have a negative sign here, which is good, because if it weren't for that, this would be exponential increase, not simple harmonic motion. So we finally rewrite again, and now we have that mg theta is equal to minus ml d squared theta dt squared. And interestingly, the masses cancel. The force of gravity depends on mass, but then again, the resistance to acceleration also depends on mass. And so what we're left with, I'll put the minus sign over here, it's more traditional, and I'll put the g divided by the L in the box. Those are just constants that you pick by setting the length of the string and picking which planet you're going to do this experiment on. And you get then d squared theta dt squared. Okay. This is simple harmonic oscillation. This is the hallmark of simple harmonic oscillation, so we know that the solution has to be a sine omega t. It just has to be, but if and only if omega is, plus some little phase, but that's set by the initial conditions. Back to the story. If and only if omega is equal to the square root of g over L, and you can try that by actually plugging it back in and showing that this has to be true. And so that means that the period of the oscillation, which is 1 over the frequency, which is 2 pi over the frequency in radians per second instead of cycles per second, is simply then 2 pi times the square root of g over L. So the surprising thing here is that the period depends only on the length and the planet that you run your experiment on.